Welcome to the 12th session in the second module in the course Signals and Systems. We have now said a lot about signals and vectors. We know how to think about inner products or dot products in the context of discrete signals and continuous signals. I mean discrete variable signals and continuous variable signals. Now we are going to address a specific question, namely, can I think of a set of perpendicular signals which could come together and form periodic signals more generally? And in fact, we will ask an even more specific question. Can I come up with a set of perpendicular signals, each of which is a sinusoid or a sine wave, and use them to form periodic signals? Now, let us understand how we could go about this whole process. So, let us consider a periodic signal with period t. In other words, if I take the axis of small t or the independent variable which is continuous in nature, I could divide this into intervals of size capital T. So, I could have minus t to 0 and then to plus t and then to 2t and then can go on. And whatever you have, say at this point is also present. So, if it is at the point delta, it is also present at the point minus t plus delta, it is also present at the point t plus delta, and it is also present at the point 2t plus delta, and this is true for every delta between 0 and t. Same value at minus t plus delta, delta, t plus delta, 2t plus delta, and so on. Now, suppose if it were possible, we could decompose this signal. So, let that periodic signal be x of t. So, xt is periodic with period t. That means formally x of t plus t is equal to x of t, and this is true for all real t. And suppose it were possible to express xt as a linear combination of sinusoids. In other words, let us take a finite, or well, not a finite, but let us take a countably infinite, a countable combination. So, suppose it were possible to express the signal xt as a countable linear combination. Now, first we need to answer why are we saying countable? Why can we rest assured that that linear combination can be countable? All these questions need to be answered. Whatever it is. Suppose it were possible to do that. So, suppose it were possible to write down this expression. What should these omega k's be? And similarly with these, what should they be? This is a question that we need to answer. We need to first establish that it is valid to think of a countable set of such sinusoids in a reasonable set of contexts. And then we need to find out how you could calculate these contributions. Now, first let me explain to you why you can be satisfied with a countable set. So, let us come back to the very drawing that we had earlier. What we will do is to put these sinusoids on each of these intervals t. So, suppose there were sinusoids sitting on the entire, you see sinusoids last forever, and if you need these sinusoids to come together, then you probably want the sinusoids to have the same property as xt does, namely they need to be periodic. But let us establish that formally. Let us establish something interesting. You see, what kind of sinusoids would you choose? You would choose sinusoids that obey the same property as the signal, namely that if any one of the sinusoids is st, then st plus t should be equal to st for all t. It is quite clear that this is the simplest choice that you can make of sinusoids. Why bring in sinusoids which do not have this property, if you can make do with sinusoids which have this property? What are sinusoids which have this property? Those that are periodic with period t. Now, which are the sinusoids periodic with period t? Essentially those, that means all these sinusoids have frequencies 2 pi by t multiplied by an integer. In fact, we can be quite happy with positive integers. There is no need to take negative integers here. So, although I have written k equal to minus infinity to plus infinity in the previous expression here, you look at it, I do not really need this minus infinity to plus infinity here. I could be quite happy with 0. Now, let us write that down. Let us write that down formally again. So, essentially we are saying x of t is of the form summation k going from 0 to infinity now, a k cos 2 pi by t times k, of course t, plus theta k. And now let us ask a question about these sinusoids. So, let us take two different k, and let us take the so called dot product or inner product of cos 2 pi by t k 1 t plus theta 1 and cos 2 pi by t times k 2 t plus theta 2, but restricted to 0 to t, the interval from 0 to t. That means essentially t going from 0 to t, only this interval. Now, you see, remember I am restricting the interval, because if I do not restrict the interval, the dot product would diverge. The inner product, you see, please remember, if I have two infinite length signals, the inner product may not converge, it may be a divergent integral, the integral may go to infinity. So, it does not make any sense. In fact, for these sinusoids, if I were to try and take a dot product, that dot product might diverge, that inner product might diverge. So, anyway, if I have these periodic sinusoids coming together to form the signal xt, I might as well see what happens on one interval, say 0 to t, and whatever is happening on that one interval is repeated in every other interval. So, I could focus my attention on one interval and satisfy myself that I know everything about what is happening on any other interval. That is why I am saying restrict these sinusoids to the interval 0 to t, or for that matter any other contiguous means all coming together one after the other, contiguous interval of size t. So, if you like, you could take the interval from minus t by 2, capital T by 2 to plus capital T by 2, anything that you like, any contiguous interval of t, but we will take it from 0 to t for convenience. Let us take that dot. So, essentially what we are saying is find out the dot product of these, dot product of let us say y1 and y2, where y1t is equal to cos 2 pi by t k 1 t plus theta 1 only between t going from 0 to capital T and 0 else, and similarly y2 t is cos 2 pi by t k 2 t plus theta 2 for again t going from 0 to capital T and 0 else. Well, that is an easy dot product to calculate. All that we need to do is to multiply these two signals and integrate between 0 and t. So, here we go, dot product of y1 and y2 is essentially cos 2 pi by capital T k1 t plus theta 1 cos 2 pi by t k2 t plus theta 2 dt only between 0 and t. And you know how to split this product of cosines. See, you know that 2 times cos capital A cos capital B is essentially cos A plus B plus cos A minus B, and therefore, this integral is integral 0 to t cos 2 pi by t k1 plus k2 times t plus theta 1 plus theta 2 dt plus integral from 0 to t cos 2 pi by t k1 minus k2 t plus theta 1 minus theta 2. Now, look at these two terms. Look at this term. This term is essentially the integral of a sinusoid of angular frequency 2 pi by t times k1 plus k2. This is the angular frequency here, and this is the angular frequency in the next one. Now, it is very easy to understand these two integrals. You have a finite number either for angular frequency 2 pi by t into k1 plus k2 or for angular frequency 2 pi by t into k1 minus k2. If k1 plus k2 or k1 minus k2 are not 0, that means if you have a finite number of cycles of the sinusoid, you see k1 plus k2 and k1 minus k2 are respectively the number of cycles of that sinusoid which are completed in the interval 0 to t. And for any sinusoid, the integral over a cycle is 0. So, unless one of these sinusoids of frequency, with k1 plus k2 cycles or k1 minus k2 cycles degenerates into a constant, the integrals are going to be 0. So, let us write that down formally. We are saying this integral, if k1 plus k2 is not equal to 0, the integral is 0. And so too, if k1 minus k2 is not equal to 0, the integral is 0. However, suppose k1 equal to k2, then the second integral essentially becomes integral 0 to t cos theta 1 minus theta 2 dt, which is essentially a constant. It is t times cos theta 1 minus theta 2. So, you see, the interesting thing here is that if you have two sinusoids, both of which have non-zero angular frequency and the two angular frequencies are different, their inner product is 0 when restricted to the interval. What do you mean by the inner product being 0? When is the inner product of two vectors 0? When they are perpendicular. Only perpendicular vectors have a 0 inner product. What have we established here? We have established that two sinusoids, both of which are periodic with period t, are perpendicular if they do not have the same angular frequency. A very important result. We shall see more in the next session how we could use this to decompose a periodic signal into its sinusoidal components. Thank you.